Hello, welcome everyone. This talk is Underwater Mars Habitats with Lee Roberts of X-Helios Corporation.
All right, thank you, Jay. Welcome everybody. I'd like to thank everybody for joining our discussion today. I'm really excited to share my thoughts about this topic with you. I'd like to thank the Mars Society for putting this on and making this possible. I know that they put a lot of hard work into preparing this convention for us and adapting it to our current circumstances. So thank you to everybody who's involved in that. So this is an idea that I developed as I was working on with a group on the Mars City State Design Competition that's being hosted by the Mars Society this year. And the group ultimately chose to go a different direction with the project that they were doing, but I felt like these ideas had some merit, so I wanted to develop them a little bit further on my own, and so I've been working independently on that. Let's see. So the fundamental question that led me down this this path was what can we do to reduce the pressure loads on habitable Mars structures? In 1971, there was an incident with the Soyuz 11 space capsule as it was undocking from the space station that it was attached to, and it experienced a catastrophic depressurization. All 3 cosmonauts on board perished as a result of that accident. And unfortunately, pressurization issues are something that are not all too uncommon in aerospace, and also, but especially in aviation, we have more experience with that. And I'll share some examples of that a little bit later on. But what I was looking at is how we can reduce the risk exposure for pressurization issues with habitable volumes on Mars. And as I think about pressurization, I think of water bottles. I'm a pilot, and a lot of times when I'm flying, I notice the effects of pressure on the water bottles that I'm carrying with me. And a lot of you are probably familiar with that as you've been flying around. When the pressure in the aircraft is the same as the pressure in the bottle, for example, if we're sitting on the ground or if we've opened the bottle and then resealed it, there's what we call zero differential pressure. This pressure is the same inside and outside the bottle. But as we climb up to a higher altitude, that pressure inside of the bottle is going to remain the same, and the pressure outside decreases. So we get a positive differential pressure. And usually with aircraft, they're designed to operate with a positive differential pressure. And they can contain that pressure. And that's a function of the engineering of the aircraft. Of course, there are limits to the extent of those engineering features. And if you've ever put dry ice in a bottle with water, that I don't recommend doing because it's dangerous, but it will expand until it exceeds the structural limits of that bottle and it will explode. Not a good thing to have happen with an aircraft, a spacecraft, or a water bottle. Conversely, if we open up the water bottle while we're at altitude and then seal it up again, and then start to descend down, then we're going to have the lower pressure inside the water bottle. And as we descend down, the pressure increases. And in this case, the water bottle actually, it collapses, it changes its shape to equalize the pressure, which isn't a good thing in any kind of habitable volume. You don't want to have it compress around you. But in our case, when I'm flying, usually what happens is that the water bottle just crushes as the pressure equalizes. And usually that happens just about the same time that I'm putting the gear down to land, and makes me think that I've broken something on the airplane, which is not a happy feeling. So ideally, it would be great if we could operate with zero differential pressure all the time, because it reduces the structural stress on our vehicle. So how can we do that? Well, here's an example like I was talking about. This is Aloha Airlines Flight 243 in 1988. They were flying. And because of structural failure due to repeated pressurization cycles, the fuselage actually failed and it flew off. One person came out of the cabin, and unfortunately the airplane was still able to land and most of the people survived. But this is not a good scenario in an airplane, much less in a spacecraft where you don't really have the option of just landing if you have a pressurization issue. So what does a scenario look like on Mars? Well, it's early enough in the conference that maybe I may be the first, but I probably won't be the last to make a reference to Andy Weir's The Martian book and movie. But we're all familiar, I'm sure, with the exploding airlock that is kind of like a bad carnival ride where you lose all your potatoes and end up having to use a whole bunch of duct tape to put everything back together. This is not a good soul on Mars. So we want to try and avoid situations like this. So the underwater Mars habitat design. Underwater habitats in general have two basic designs with regard to pressurization, either closed designs or open designs. Closed design is going to be similar to what you might find on a submarine. Typical submarines, military type submarines, where the internal pressure is isolated from the external pressure by means of hatches. And this is similar to the third picture of the water bottle that I showed, where the pressure outside is higher, but with submarines, they're built structurally to be able to contain that pressure and have a lower pressure inside of the vehicle. And they do that by means of a series of hatches, similar to this one, that keep that pressure out. And the challenge, one of the challenges with this type of a vehicle or habitat is that entry or exit has to be through an airlock that allows for equalization of the pressure between the internal volume and the external volume. And we're probably all familiar with that principle of an airlock. It has two doors. You close one on the inside, the pressure equalizes, and then you open the door on the outside, and vice versa if you're entering into the vehicle or habitat. The benefit, or one of the benefits of this particular design is that occupants live in a one atmosphere environment, and so they can make an emergency ascent to the surface without having to worry about decompression. They're basically taking their environment with them. And that's kind of similar to what we experience with space stations and most space vehicles. An open pressurization design is kind of similar to what we saw in C-Lab. C-Lab 2 was in service back in the mid-1960s. And in this situation, the internal pressure is equalized with the external pressure surrounding the vehicle by means of either standpipes or a moon pool. And on this picture right here, you can kind of see where the moon pool is on C-Lab 2 right down here. And that moon pool, I'll show an example here, is basically just an opening that comes from underneath the vehicle, underneath the habitat, and it equalizes that pressure between the internal volume and the external atmosphere. And one of the nice things about this is that you can enter and exit the water in an underwater habitat without having to equalize, because the internal pressure is already equal to the external pressure. One of the disadvantages is that emergency ascent requires decompression. So you usually, if you have any kind of an emergency and you have to do an emergency ascent, you're going to have to spend some time in a decompression chamber or a hyperbaric chamber to equalize the pressure. But one of the advantages is that there's minimum risk for catastrophic structural failure because the pressure is equalized between the internal and external atmospheres. And so there's very minimal structural stress on the vehicle itself. So what this looks like in a Mars situation, on Earth, we can calculate the amount of water that is required to exert a certain amount of pressure at different depths. Generally, this works out to be about 1 atmosphere or 1,013 millibars for every 10.3 meters of water depth. And it can be calculated using the equation H equals P over rho G, where height, H is the depth of the water, P is the pressure, rho is the density of the water or other substance, and G is the gravity. On Mars, because the gravity is less than it is here on Earth, instead of every 10.3 meters of depth for 1 atmosphere, it would be, we'd have to have 27.15 meters of depth with water to exert 1 atmosphere of pressure on a habitat or a vehicle. And at that depth, with an open pressure habitat design, we can have 1 atmosphere of internal pressure while maintaining 0 differential pressure between the internal and external volumes of the external atmospheres or environments of the vehicle. And so that significantly reduces the amount of structural stress that we're placing on a vehicle or on a habitat. So for every 100 meters of habitable volume, 100 square meters of habitable area, that's going to require a depth, a volume of 2,715 cubic meters of water. And that's slightly more than the amount that is required to fill an Olympic-sized swimming pool. So if you can imagine all that water being placed on a floor area of 100 square meters, that's how much water would be required. So I know there's an obvious question. The elephant in the room is, well, hey, you know there's no liquid water on Mars, right? And that is an excellent point. I will concede that. But more relevant to this discussion is, why do we not have liquid water on Mars? And it has to do with the triple point of water. So water, any substance that can go from one phase to another is going to have a triple point. So the triple point is the combination of temperature and pressure at which the 3 phases of a substance can coexist in thermodynamic equilibrium. For water, what that means is that if you can see my pointer right here, the triple point of water occurs at 273 Kelvin and 612 pascals of pressure. So if the pressure is lower than that, water can't exist in a liquid state. It's going to sublimate directly from a solid to a vapor and back again as the temperature changes. It never transitions through a liquid phase. And in order to have water in a liquid phase or any other substance, we have to raise the pressure above that triple point. On Mars, the average surface pressure at the mean radius is only 636 pascals. So that's just slightly above the triple point for water. That leaves a very narrow window of temperatures where water can exist at those pressures. It's only a couple of degrees. So if we can raise the pressure just slightly, we can increase the size of that window so that water exists in a at those lower pressures, or we can increase the window of temperatures where we can have water. So if you've ever flown across the country, especially in any of the oil producing areas of the country, or into any major airports, you've probably seen these petroleum farms. And on these petroleum tanks, they have these floating roofs that move up and down as the volume of fluid inside the tank changes. And this is one way that we might be able to adjust the pressure on a reservoir for water on Mars. So the floating roofs are used to minimize the volume that is available above the surface of the fluid. And in the petroleum industry, they primarily do that to decrease the risk of fire and also to limit evaporation losses. In this diagram of a tank here, you'll notice that there's this floating roof. It moves up and down, and it's hollow inside so that it provides buoyancy to move up and down. And then there's a rubber seal that runs along the outside edge of the roof, and it seals against the walls of the reservoir, or the walls of the tank. And that's an important feature to prevent evaporation and boil off of the liquid that's inside. So to increase the surface pressure on a Mars water reservoir by 50%, a floating roof like this would have to have a mass of at least 85.5 kilograms per meter squared. And the idea that I had is to build a tempered glass roof that consists of panels, triangular panels, joined by flexible pontoons. And if these panels are 10 centimeters thick, made out of tempered glass, they have a mass of approximately 250 kilograms per meter squared, which imparts a pressure of 930 pascals on the surface of the reservoir. And in combination with the atmospheric pressure on Mars, that is adequate to prevent boil off or evaporation of the water at temperatures up to 308 degrees, or 308 Kelvin, which is about 35 degrees Celsius. So the panels are joined by a series of pontoons that provide buoyancy and allow them to float on the surface of the reservoir. And to cover a reservoir that is built inside of a crater approximately 1 kilometer in diameter, you would join these panels together with these flexible pontoons, and then a skirt around the outside of the reservoir would provide a seal against the crater wall. And once you have that in place, this roof with the skirt around the outside edge, the crater would be gradually filled with water underneath the roof. And to fill a 1 kilometer diameter crater to 27 meters of depth requires about 8.5 times 10 to the 7th meters cubed, or 8.5 times 10 to the 10th kilograms of water. So it's a lot of water, but it would provide that 1 atmosphere of pressure at 27 meters of depth. So there are obviously some disadvantages with this idea, but there are also some significant advantages. The way I have this set up, I kind of paired a few of them together, and then some of them kind of stand alone. So first of all, on the disadvantage side, you have a large scale project that requires developed industry and extensive resources. You have to have the means to produce these panels, the skirts, to produce the water, and to produce the habitats. All of that needs to be in place, which is a pretty daunting task. It's not a small feat. On the positive side of that, it's going to support a large scale population. And that kind of goes into the next points here regarding economies of scale. The benefits of this project are subject to economies of scale, which means that a larger settlement is going to be more suitable for this concept. It doesn't really work for a settlement of, 15, 20 people. That's not going to be economical. You're probably going to be looking at something that's going to support hundreds or thousands of people, if not more. The upside of that is that once you get this going, growth is inexpensive because of those economies of scale. And so you can expand this for a relatively low cost once you have it going. There are possible structural complications due to corrosion. That's an issue with any kind of structures that we have underwater. But that's also balanced out by the fact that we've reduced the stress significantly on the structures due to minimal differential pressure. Few standalone disadvantages. We have potential for damage to panels and roof components. The situation that occurs to me is what happens if we have a meteorite strike one of these panels or strike a portion of the roof? How fast is the water going to boil off? How are we going to deal with that? And so we would have to have mitigation measures in place for potential roof damage. One of the advantages of that particular design is that because the panels are modular, it allows you to replace 1 or 2 panels at a time without having to replace the whole roof. So that's kind of one method that I looked at for mitigating that concern. We have an issue of possible boil off due to inadequate sealing of the roof and of the skirt around it. And so we need to make sure that everything is sealed tight. We also have a concern for possible seepage through the crater floor and walls because it takes so much energy and effort to produce water on Mars and to refine it, if you will. We want to minimize the loss, both through boil off and through seepage. And then also occupants in our habitats are separated from Mars surface exploration because of the inherent boundary between the habitat and the Mars surface. So we would have to have an efficient means of transitioning between those two environments. On the plus side, because of the zero differential pressure, this allows for non-spherical or cuboid structures. So we don't have to have big tubes that don't efficiently use the volume that's available there. It provides for thermal regulation because the water serves as a heat sink, and so you're not going to have extremes of temperature with the diurnal cycle on Mars. It also may support agricultural production of aquatic plants and animals, so you may be able to have underwater farms that raise seaweed or fish for consumption as a food source. And this is my favorite advantage. It provides significant shielding against GCR and SPE charged particle radiation. I was looking for some specific numbers on this. I couldn't find a really good reference for it. The best I could find, and somebody can correct me on this, my best understanding is that for every ½ meter of water depth, you're going to get about a 50% reduction in charged particle exposure. And so for 27 meters of depth, you're going to have almost a negligible exposure to charged particles. So in conclusion, underwater habitats, I believe, present a significant benefit for large-scale settlements in the distant future on Mars. This is something that we're not going to see right away when we go to Mars. It's something that's going to happen as we get to larger populations on Mars. But with any kind of technology, as a general rule, the rate of population growth in a Mars settlement is going to be hastened if the technology is developed before it's actually required. And so this warrants some investigation right now. And so I'm proposing to conduct a series of research projects to explore the practicality of underwater Mars habitats. I'm going to start by conducting some small-scale roof design experiments and look at their effectiveness. And then I think it's also important to look at how water boils off with various exposure areas to a vacuum, and see how quickly that happens and what the risk is that's associated with that. And then eventually, I think that the natural progression of those experiments is to eventually do a high elevation underwater habitat at a high mountain lake that has analogs of an analog environment at 1 atmosphere of pressure underneath a high mountain lake. And so that's what I'm looking at doing, the direction that I'm going with this project. So this project is really a work in progress. I really appreciate any suggestions or ideas that can help it along, especially with regard to potential research and development ideas. And I'd like to thank you all for your attention and your interest, and welcome any questions.
A question from Marco. How do underwater habitats compare to lava tubes and regolith in the mitigation of radiation?
That's a great question, Marco. I'm not sure how they would compare in terms of radiation mitigation. That's not really my area of expertise, but it's an excellent question. I think that you would have to look at how deep the lava tubes are and how much, to really get a good comparison, you have to look at the actual thickness and the amount of protection that's being provided by each one.
Okay.
Hi there. Suggestion regarding your future research, is there any intention to use the deep water pool at the biosphere 2 to conduct any of the research?
I'm sorry, say that again, the deep water pool at the biosphere 2?
Yeah. Would that provide any usefulness in researching towards this goal?
That's a good question. I went down to Biosphere 2 last year, and there's some really interesting stuff there. I think one of the things that is a particular benefit with this is that it provides a large volume of water. You know, a lot of times when we think about how much water a person needs to survive, we're just thinking about how much they need to drink, how much they need to wash their hands, or, you know, do the basic biological functions. Rather than what's actually required to sustain them and everything that they do. For us, I mean, that means manufacturing, it means agriculture, it means production. It's not just what we need to drink and wash our hands and cook our food. And so that's one of the problems that I think that they ran into at Biosphere 2, is that they didn't have an adequate volume of water to support the processes that were going on inside of that closed ecosphere. And so we really need to look at how much water do we really have to sustain life. I don't know that that exactly answers your question, but I think that the research that's been done there at Biosphere 2 provides some great benchmarks and foundations for developing this project. Thank you for your question.
Brilliant. Thank you for answering my questions today, and all the best.
I have a question. Are there any plans to build more facilities like Biosphere 2, perhaps underwater on Earth, in order to facilitate your research?
I don't have a plan for that. What I'm doing is a little smaller scale than that right now. Eventually, I would like to do something that is not quite on the scale of the the C lab that I showed you, but something just a little bit smaller than that. Again, in a high mountain lake. But most of the biosphere is a pretty large scale project, and to build something on that scale underwater would be pretty monumental. So.
Another question, since everybody's quiet.
Sure.
What are some of the potential hurdles that you expect to encounter along the way?
Money. It's always money.
It's usually the case.
In addition to money, I think as much as anything, it's a question of finding people who have a common passion and interest in exploring this and supporting this idea. And the other big hurdle, I think, is that it's something, like I said, this is a long-term project. It's not something that's going to happen right away. You know, we're looking at supporting populations of thousands, not tens. And so until you get to that point where you have that large of a population on Mars, it's difficult to maintain the drive behind this project until it reaches that level, I think.
I have another question for you. Oh, sorry, go ahead.
Yeah,
Sorry, I was just saying thank you for another great answer.
yeah, you're welcome.
Are you familiar with Asgardia?
I'm not.
So Asgardia was established 4 years ago by a Russian scientist named Igor Asher-Bailey. And what it's done is basically it's pulled together millions of people around the world who normally wouldn't care about science, especially space sciences. I think one of the biggest hurdles we have is if we had the funding that sports has, we'd already be living like Star Trek, basically. So
You're not wrong.
Getting the common person interested and excited about space sciences is kind of half the battle. So Asgardia has done amazing work with this. They've already launched a satellite, and they got loads of people to work on that weren't scientists. And I've just seen this. I work with an organization called Galaxis, and our main goal is to get people excited about it. And we worked for 12 years. And, you know, we get very few people, and then Asgardia came along and it just blew up everywhere. It's a pretty amazing organization. So that has pulled together scientists, politicians, housewives from across the world, you know, just random people. And it might be something interesting for you to network with.
Yeah, absolutely. That's very interesting. I'll definitely have to look that up.
Asgardia.space, and he actually runs Room.
Space.
Yeah, Room, the space magazine.
Okay. Yeah, I will look at that. I agree that one of the great challenges that we have in general with trying to go to Mars, with trying to settle Mars, is that we have, as a people, we have a hard time getting on the same page and coming to a common direction, a common purpose. And until we can not completely overcome that obstacle, but at least make some progress in that direction, it's going to be hard for us to really make substantial progress.
Finding the relevancy, I think, is the problem. I often get asked, you know, why go to space when we have so many problems on Earth? But most of our problems on Earth are resource scarcity, and space solves most of those problems. So if we can convince people that, you know, space will end resource scarcity and pretty much, you know, provide whatever we need, I think then more people would be interested.
Yeah, absolutely. Thank you for your comments.
Yeah, I want to add something to that too.
Go ahead.
Yeah, so I'm a member of the Planetary Society. I don't know if you're familiar with them, but
Yeah.
we advocate for space, and we actually go and meet with our representatives. So one of the most important things you can do, just for the listeners, is to actually call your members of Congress and say, hey, we're interested in space. You know, the more money, like you were saying, and funding that we get, the more projects that we can do, the more research that we can do for science, and you know, the joy, the love, and passion.
Thank you, Marco. Yeah, that's a great organization for people to be involved in, to kind of take advocacy to the next level.
So, is water the best liquid to work with, or are there other chemicals like alcohol that could work better?
I was actually just considering alcohol yesterday as an analog for water here on Earth, because I was trying to find something that would have a triple point that's close to atmospheric temperatures and pressures, but that would behave the way that on Earth that water will on Mars. I think the water is the best liquid for this function on Mars because of it's something that we need anyway, and it's something that's already there. We just have to again refine it, and there are some different ways that we can source the water, but that's kind of the direction that I approached this from, was that it was something that we would already have available to us and that we would already need. But that's a great question. It's interesting that you and I were kind of on the same wavelength with that, Josh.
Thanks.
Well, thank you everybody for your comments and questions. I have a few in my email here also, and I'll answer those in just a little bit. I do need to get going to another room here that I'm helping out with, but please feel free to reach out to me, and I will be available here on the conference also on one of the Slack channels. I'll open up a Slack channel to continue the discussion. Thank you very much, everybody.